For our first example in this section, we're going to look at the difference between using something like washers versus using shells. And I want to show you the differences in terms of how we measure things. So first, we're going to take a look at the washer version of this. So what we have here is a question that asks us to find the volume of the solid obtained by rotating the region bound by the curves y equals x squared and y equals root x about the line x equals -1. So y equals x squared is the purple curve, y equals, oops, can't see it, I guess I cut it off there. Y equals root x is the black curve here. And then the vertical line x equals -1 is over here, and we're going to rotate about that particular vertical line. So when we do that, if we rotate here and we decide to use washers, either way, we're going to slice perpendicular to our axis of rotation. So when we come through here and slice perpendicular to our axis of rotation, we're going to get a horizontal strip out of the middle of this shaded region. And as we rotate, that region is going to generate a washer. Why a washer and not a disk? For the simple fact that this red region here doesn't actually touch the axis of rotation. So we got this gap in the middle. And as we rotate around anywhere in that red region in our shaded area, we're going to be swinging around the axis of rotation. So as we go here, some of the key features are the fact that these are measured dy in thickness, and we have a washer. And so using washers, what is important here is our form that we start with. This is the integral from a to b of pi times capital R squared minus little r squared dy, and that's where I like to start. So we'll just regurgitate a general formula. And now we got a few things to find. We got to find the limits of integration, a and b. Let's start there. The limits of integration a and b are with respect to the value y. So our lowest horizontal slice will be down at y equals 0, and our highest horizontal slice will be up here at y equals 1. So those will be our limits of integration. Y equals 0 to y equals 1, pi. We have our outer radius squared minus our inner radius squared, integrated dy. Let's figure out what that is. Remember, the radii are measured from the axis of rotation over to the curve. So my first axis of rotation is going to be from the axis of rotation out to the curve y equals x squared. Now, remember that generically, when we measure from the y-axis horizontally over to a point, that distance is x. And this distance here, if we count it out on our fingers and toes, is a distance of 1. So one way that we could figure out what capital R is we could say R is equal to 1 plus x. Now, that's from a geometric standpoint. That's me eyeballing it and try to measure these things, which isn't always the best way to do it. However, another way that we could do this is we could use right minus left. Now, if we do right minus left, the right side is the curve y equals x squared, and the left side is x equals -1. So again, the right curve is y equals x squared, and the left curve is x equals 1. So what do we have here? Well, what we have is the right side, x, minus the left side at -1, or x minus -1, which also turns out to be 1 plus x. But there's a problem there. In both of those cases, we're unhappy. Why? Because we want this to be done with respect to y. So on this curve, what is an x worth? Well, if y is equal to x squared, then in terms of y on that curve, x is equal to the square root of y. Now technically it's plus or minus the square root of y, but since we're on the right side of that curve where everybody's positive, we're going to use the positive version. And so this tells us then that our capital R is equal to 1 plus the square root of y. Or you could come back here and say that this is the curve x equals the square root of y, and then it's the right side, root y, minus the left side, negative 1. And let me actually rewrite that a little bit differently. This is x equals root y minus x equals negative 1. So again, right minus left. And I'll put a right and left there. So either way, we get 1 plus the square root of y. For our other limit of integration, I'll do this in blue. Sorry, not limit of integration. Our other radius is measured from the vertical line, x equals negative 1, over to this particular curve. Now, this particular curve is on y equals root x, or x equals y squared. So this is y squared. This is x equals negative 1. I should say not just y squared, but x equals y squared and x equals negative 1. So what we have is x minus x, but on the right we have y squared, and on the left we have negative 1. So little r is y squared minus negative 1, which is y squared plus 1. Okay, so now everything is in terms of y, and we can integrate this. I'll factor out a pi. This is the integral from 0 to 1. I'll have to FOIL this guy out. Let's see. Then I square that, I'll get 1 plus 2 root y plus y minus, when I square, this is y squared plus 1 squared. It'll be y squared, sorry, y to the 4th. Come on. In parentheses, y to the 4th power plus 2y squared plus 1 integrated dy. And I'll rewrite this just a little bit. This is pi 0 to 1. Let's see, I'll have 1 minus 1. And those will cancel. And everything else is a different exponent on y, so this will be a 2y to the 1/2 power plus y minus y to the 4th minus 2y squared dy. And when we integrate that, the antiderivative will be, let's see, 2 times 2/3 y to the 3/2 plus 1/2 y squared minus 1/5 y to the 5th power minus 2/3 y cubed evaluated between 0 and 1, which will be pi times 4/3 plus 1/2 minus 1/5 minus 2/3. And when we plug in 0, we'll get 0. So let's see, what do we have here? I'll just continue this on the right side. Let's see. This will be 4/3 minus 2/3 is another 2/3. So we have thirds, halves, and fifths. So our common denominator is going to be a 15th. And let's see, by 5, that'll be 10. No, not 15ths. The common denominator, I better write this out before I screw it up. Hold on a second. Pi, and then this will be 2/3 plus 1/2 minus 1/5. So what are we talking about? 30ths. So this is pi over 30. And we'll have to multiply that first numerator by 10. So that's a 20. The second numerator by 15. And the third numerator by 6. And so 29 pi over 30. And hopefully I haven't made a mistake there. Now, let's take a look at this same problem again using the shell method. So, example number 1, now with shells. So let's draw this region again really quick here. Let's see. Not to scale. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, something like that. We have y equals x squared. We have y equals root x. That's the point 1, 1. They both intersect at the origin. And then over here, off to the side, not to scale, is the vertical line. Come on. X equals -1. And we're going to be rotating about that axis and this particular region. But this time, and watch how we do this, this time we're going to be generating cylindrical shells. So the first thing I'm doing is I'm drawing a cylindrical shell wrapped around this axis of rotation. And for my cylindrical shell here, this width is the thickness, and that is a dx thickness. So here we have shells are integrated dx, which in contrast to here we had our washers dy. So you'll notice that even though we're finding the same volume, we're using a different technique, and in this different technique we have a different variable of integration. So the first thing I'm going to do is regurgitate that general formula. The general formula for shells is the integral from a to b of the circumference of the shell times the height of the shell times the thickness, and we'll add them all up. And I'll be able to factor out a 2 pi. X is going to run from x equals 0 to x equals 1 in the x direction there. 2 pi, and then I have the radius, r, and the height, h, integrated dx. So let's talk about what those are. Now, that means that our approximating strip in this region is going to be vertical. That's this strip here. And it's going to have a certain height. From section 5.1 in the area between curves, that height is going to be the top curve, square root of x minus the bottom curve. And the radius is going to be still the distance between the axis of rotation out to the shell wall, or that vertical strip. Now, this is an arbitrary point, x comma y. And in terms of x, it's located at x. Over here is x equals -1. And this is right minus left, x minus -1. Right minus left. Or if you like, this is one solid unit of distance, and here to here is x. And so we're just adding those two together, if you want to think about it that way. So what do we have? Whoops, I wrote 2 pi twice there. Factored out that 2 pi. So this is equal to 2 pi times the integral from 0 to 1 of x plus 1 times the square root of x minus x squared dx. We are going to have to FOIL that out. I'm going to rewrite this radical x as x to the 1/2 power. So the result is 2 pi, integral from 0 to 1, and as we FOIL, I'll get x to the 3/2 power minus x cubed plus x to the 1/2 power minus x squared dx. And the antiderivative there should be relatively straightforward. This is 2/5 x to the 5/2 minus 1/4 x to the 4th power plus 2/3 x to the 3/2 minus 1/3 x cubed, evaluated between 0 and 1. And we have 2 pi times 2/5 minus 1/4 plus 2/3 minus 1/3 minus 0. If we clean that up a little bit, that's 2 pi times 2/5 minus 1/4 plus 1/3. The common denominator for 5, 4, and 3 is 60. And I'm kind of running out of room here. Let me just move all of this over just a little bit so that I can not necessarily start a new page here. And this is equal to 2 pi times, let's see, 24 over 60 minus 15 over 60 plus 20 over 60 is equal to, let's see, 24 and 20 is 44, minus 15 is 29 pi, and then the 2 will go into the 60s 30 times. And I'm left with 29 pi over 30, and I'm happy about that because that's exactly the same value that I got using the washer method. So there's some deconstruction of how to set these things up, and you really want to pay close attention to, when you review, you want to pay close attention to how I generated these values. So really quick, what I did in order was, number 1, I decided what technique I was going to use. I drew that little approximating geometry around my axis of rotation, and then decided what the thickness of that was, and that told me what variable I was going to use and what form I was going to use. And then I systematically went through and found all the missing pieces for that form, and then I integrated. Not sure why I put a 1 there, but that's the idea.